Greetings. We will begin unit 2 today. This is on angular momentum in quantum mechanics. We have already introduced angular momentum as such in unit 1 because the whole machinery of the rotational symmetry of the hydrogen atom was intimately geared to the angular momentum algebra. So we will develop it further, but in a more formal way now, and some of the results that we had sort of anticipated or assumed, we will establish them more rigorously now. In particular, there are some questions which sometimes are quite interesting. For example, one might ask, is relativistic mechanics needed only when you are dealing with particles which are moving at extremely high speed, like relativistic speeds 0.9 c, 0.8 c, okay. These are relativistic speeds, and if you are not dealing with very high speeds, do you need relativistic mechanics at all? This is the question which sometimes people ask, and very often people believe that you do not really need relativistic mechanics. Very often you say that, okay, you do not need quantum mechanics if you are dealing with macroscopic objects. If you are dealing with big objects like this water bottle, the laptop, the furniture in this room, okay, motion of trains and aeroplanes and so on, you do not really need quantum mechanics. You need only when you are dealing with small tiny particles, atomic particles, elementary particles and so on. One often believes, or one often asks, do you really need relativistic quantum mechanics if you are dealing with electron spin, because you can deal with half angular momentum quantum numbers in non-relativistic mechanics. So do you really need relativistic quantum mechanics? So these are some questions which people ask, and one really needs very precise answers, and I believe that you already have some of these answers, and if you do not have these answers, I expect you to find these answers in this class. Now, angular momentum in classical mechanics is a very well known thing, and you have the Kepler problem, the two body problem, and angular momentum is defined as r cross p, and it has got a magnitude which is r times the momentum. So it is sometimes called as the moment of momentum for this reason. You can see that it can be written as the product of the moment of inertia and the angular velocity and the angular speed in a form which is very similar to linear momentum, which is the product of mass times the linear speed. And then in the Bohr model of quantum mechanics, when you go over to quantization, it does appear once again as this line integral of p dq, which is quantized, which was done in Bohr's model of the old quantum theory, but that is valid only for periodic orbits, not for open orbits. Now, if you quantize this, you replace the dynamical variables by corresponding operators, and then instead of p you get the quantum operator, which is minus h cross gradient operator. This is one way of quantizing the system as such. What it leads to is that when you connect it to the generator for rotations, which angular momentum is, and you know this from classical mechanics as well, what happens is that if you perform rotations about x axis and y axis in one order and then do it in the reverse order, you do not get the same result. I refer to this exercise in our unit 1 as well. As a result of this, the operators in quantum mechanics Jx and Jy do not commute. The rotation group is therefore not abelian, and this commutation relation is what we proceed to take as the very definition of angular momentum in quantum mechanics. Okay. So the definition of angular momentum is quantum mechanics is given by these commutation relations. I was told by a student in this class that she found that j cross j turned out to be 0 and that j comma j also turned out to be 0 while doing the algebra. So, I think it is obviously some careless mistake that she would have done, and I hope that all of you have worked this out to convince yourself that the quantum j operator does not commute with itself. Okay, the commutator of j with j is not 0, it is I h cross j. Likewise, the cross product of these two operators is not 0. So, these are equivalent definitions of the angular momentum, and it has got these three attributes, that it is a quantum creature, it is a vector creature, and it is an operator. So, all of these three attributes must be respected when you deal with the angular momentum operator. Now, we have already acquainted ourselves with the fact that these are generators of rotations and then of the SO3 group whose rank is 1, whose Casimir operator is j square, and because j square commutes with every generator, j square and jz can be simultaneously diagonalized. What it means is that these correspond to simultaneous measurable quantities, they are compatible measurements. Okay. You can therefore have simultaneous eigenvalues of these two operators. You can perform a measurement of j square, then perform a measurement of jz, then come back and perform a measurement of j square and do it in any which order, and the eigenvalues will remain intact, because what a measurement does to a quantum system is that the system collapses into an eigenstate of the measurement, right, and once it collapses into that eigenstate, it stays in that as long as it is not disturbed by another measurement which is not compatible with this. Okay. If it is disturbed by a measurement which is not compatible with this, then it will not remain in that pure state, it will have to be expressed as a linear superposition of the entire basis set. Okay. So, this is what it means, and as a result of this, the eigenvectors can be labeled by two quantum numbers, both of these are good quantum numbers j and m, and what we have done is we are going to find out for ourselves what this j should be and what this m should be. So, I am aware that you have some earlier knowledge about this from your previous courses. You know that j can be either 0 or half or 1 and 3/2 and so on. You also know that m goes from minus j to plus j in steps of 1. What we are going to do is to establish this on first principles. So, we will not assume that we already know what j will be like. We are not going to assume that we already know that m goes from minus j to plus j, but we will do a simple analysis and discover that this is what it will have to be, it cannot be anything else. So, it is not something like a result that we have to take for granted or make an assumption or anything. We will see from very simple analysis, and the most beautiful thing about this is that in physics you like to get results based on the smallest number of assumptions. You should not add any additional assumption, and what I am going to demonstrate here is that the algebra of angular momentum that you see on the screen, that just the definition of angular momentum, it is defined by how its components commute with each other. This is sufficient to lead to the consequence that j will have to be a number which is either 0, half, 1, etc., and m will have to be a number which is from minus j to plus j. So, this will come automatically just from the very definition of angular momentum which is here. Nothing else has to be used, nothing else has to be invoked, nothing else has to be assumed. You have already done the Schrodinger equation for the hydrogen atom, and from the solution to the spherical harmonics you know that when you are dealing with orbital angular momentum, L can take these values. Now these are integers, there are no half integers here when you are dealing with orbital angular momentum, okay. There is no half integer, but in general these half integers are admitted in the angular momentum algebraic scheme, and we have to find out from where these really come. There are some related questions as to how we get this. When we say that the electron is a spin half particle, what exactly do we mean by this? What does it mean to say that the spin is up and the spin is down? These are some related questions, and we will look for very rigorous answers to these questions, and all of these questions will be answered based on this very simple defining relationship. Nothing else is needed, you do not have to make new assumptions or additional postulates. So these are our basic eigenvalue equations. We know that J square and Jz will have simultaneous eigenstates, they can be simultaneously diagonalized. So you can write eigenvalue equations for both of them and use the eigenvalues to label the states, okay. This is what we have learned already in unit 1, that you label state vectors by eigenvalues of those operators of which these are eigenvectors, right. So the eigenvectors are labeled by J and M, where the labels come from the eigenvalues. From the eigenvalue I extract the dimension separately. So this is J square, so there will be a dimension of angular momentum square in the eigenvalue, which I extract in units of h over 2 pi, and then I am left with a residual eigenvalue, which will be just a number, which will be a dimensionless number, whatever it is, which I call as some function of j, and use that label j to describe the vector. Likewise for Jz, I have extracted the dimension h cross over here, which is the angular momentum dimension, which is h over 2 pi rather than h, that is just a matter of convenience, and then there is an additional label which is m, but at this stage I really do not know what m is, nor do I know what j is, that is something which we have to figure out, okay. There can always be an additional quantum number like lambda, it will come from eigenvalue of some other operator with which j square and jz both commute, right. So, and there can be one or more such operators. So lambda represents the family of all these additional operators which also commute with j square and jz. For the hydrogen atom we already know it is the Hamiltonian, but it could be something else. So we ask what can be j and m, they can be only what they will turn out to be, cannot be anything else. So we will find out what j and m turn out to be. Now we know that in this basis j square and jz both must be diagonal because they can be simultaneously measured. So if you determine a matrix element of j square in the jm basis, it must be diagonal in the j index as well as in the m index, that is what is meant by a diagonal representation. So both of these matrix elements, matrix element of j square as well as the matrix element of jz, must be diagonal in j and m index, which is what I have represented here. The rest of it is coming straight from this h cross fj and h cross m. Fair enough. So we know that. Now if we construct these operators j plus and j minus, which is the sum and difference of jx and ijy, then it is clear that j square will commute with j plus and j minus, but jz will not commute with j plus and j minus. And if you just use the original algebraic equation, and this is the point which I am emphasizing repeatedly, that all you are using is the defining relationship for the angular moment, that jx comma jy is equal to ih cross jz, okay, or j cross j is equal to ih cross j. Just these definitions, do not use anything else. do not use what you know from other sources, just use this, and using this you find that Jz does not commute with J plus and J minus, and using these basic commutators between Jx and Jy you can easily show that this commutator is not 0, rather it is plus or minus H cross J plus or minus. Okay, so this is a very simple algebra that you can work out, all you have to do is to plug in the original commutation relations. What it means that if you take the matrix element of the left hand side, which is here in two states J double prime, M double prime and Jm, it is equal to the matrix element of the corresponding matrix element of the right hand side, and I am taking the case of J plus just to demonstrate this argument. So here you have this relation, this matrix element is equal to the matrix element of H cross J plus, H cross is the constant which I have extracted out. I can always insert a unit operator here, I can insert a unit operator here as well, you know how to resolve the unit operator. So you resolve the unit operator in this basis J prime M prime J prime M prime, this is the Ket-Bra summed over J prime and M prime, right. This is the resolution of the unity which I have exploited, and what you immediately find is that when you look at this matrix element, this is a factor here, the first term is the product of two scalars, the first one will require a delta Jj prime because Jz is diagonal in the J index. Okay. Likewise, the second term requires orthogonality of J prime J double prime because J plus is also diagonal in the J index. Okay. So we can exploit this, and what it essentially means that the function J and J prime and J double prime, these must all be equal to get non-trivial solutions, they must be equal to each other, that automatically follows, and this would be the case on the right hand side as well. So this J and this J double prime must also be equal. So here we have the main result, and now we proceed by carrying out the sum over J prime, and we now have this orthogonality between J and J prime and J prime and J double prime. So you are left with a sum over M prime, all the sums over the J indices have been carried out, and what remains will have all the J's, J, J prime, J double prime, all of them must be equal to each other, for which I use a single symbol which is J itself. Okay. So let us take this result to the top of the next slide here, and now you have Jz operating on J M prime and Jz operating on M double prime over here. So the result from the first one is M prime H cross from the eigenvalue equation, right. So this M prime H cross comes here, from here you get M double prime H cross which comes over here, there is a minus sign which drops here, okay. And now you can see that there is an orthogonality between M and M prime, and then you can sum over this M prime to exploit that orthogonality and reduce this whole sum. So it is very straightforward, you get this orthogonality between M and M prime because these are orthogonal states, orthonormal states, and now you exploit this orthogonality, carry out the summation over M prime, and you are left with only one term now. And what is the term? It is MH cross times this element in which M prime has been set equal to M, and in the second term you have summed over M prime, and the only term that survives is the one in which M prime is equal to M double prime. So you have got M double prime over here, okay. So this is the result that you get. Now notice that this factor matrix element is common to all the three terms, it is the matrix element of J plus in corresponding states in all the three terms. So, you can factor it out as a common factor and you get a very simple relationship which is the product of two terms which vanishes, which means that at least one of them has to be 0, and the condition that the matrix element of J plus is not 0 is that the other factor must be 0. So, essentially it means that m minus m double prime minus 1 must be 0 for this matrix element of J plus to be non trivial, otherwise it is a trivial 0. In other words, m must be equal to m double prime plus 1, and this is a necessary condition that emerges from a very simple analysis which offers this interpretation to the operator J plus as a raising operator, because this the index on the left must be in excess of the index on the right by unity. That is a necessary condition that follows. I will leave it as a very simple exercise for you to find out that J minus is a lowering operator. Do the same analysis, it will come automatically. So, now you know that you have a non trivial value for this matrix element only when this index is in excess of the index on the right side by 1. So, you plug this in as m plus 1 when this is m, and this will be some scalar. It will have dimensions of angular momentum which you extract in units of h over 2 pi, and then you are left with an unknown quantity which is some number lambda m, and we have now to find what this lambda m must be like. Okay. So, if you now take the Hermitian adjoint of this relation, what is a Hermitian adjoint of this relation? It is what you have over here term by term. So, you get lambda m star h cross. There is no new algebra which is introduced over here, all you have done is to determine the Hermitian adjoint of the previous relation. So, what it essentially means is that J plus would raise the m index to m plus 1 and scale the new vector by lambda m h cross. It will not give you an eigenvalue equation, it is not an eigenvalue equation, it gives you a new vector whose m index is in excess of the previous one by unity and which is scaled by a factor lambda m h cross, but we have to find what lambda m is. This belongs to the orthonormal basis. Likewise, J minus, you have an exactly identical relation in which J minus lowers this index by unity. From m plus 1 it will go to m and it will be equal to lambda m star h cross, which has come from the adjoint relation. So, J minus reduces the m index by 1 and scales it by lambda m star h cross. Once again the angular momentum has been factored out. Alright, notice that when J plus operates in this index and the subscript on lambda is the same, whereas in the case of J minus it is different. Here this index is m plus 1, but the subscript on lambda is 1 less. So, keep track of that. Okay. Now, this is the basic commutation relation which again comes from the basic fundamental definition of angular momentum operators. So, it is very easy to establish. You take the matrix element of this, a diagonal matrix element in the state Jm, which is equal to the corresponding diagonal element of Jz. You separate these two terms. So, you have two matrix elements on the left hand side, and now you operate on Jm by J plus J minus term by term, first by J minus which will lower the index, and then by J plus which will increase the index. You do it stepwise. So you know how to do that because J minus lowers this index by 1. So J minus would lower this index to M minus 1 and the subscript on lambda will be M minus 1, it is the same as this index over here. So this index will be lambda M minus 1 star, whereas in the second term over here J plus operating on J m will give you lambda M h cross. So this subscript will be M. So this is lambda M, this is lambda M minus 1, keep track of that. Now you work with J plus, and J plus when it operates on this it will increase this index from M minus 1 to M, but then it will give you the same index as was before. So it will again give you lambda M minus 1. So in the first term you get lambda M minus 1 star lambda M minus 1, you will get this modulus square of lambda M minus 1 in the first term. Likewise in the second term you get the modulus square of lambda M. Of course there are h cross square terms appearing everywhere, there is h cross square in the first term, h cross square in the second term, and h cross square in the third term as well, because when Jz operates on Jm you get mh cross. So that h cross with this h cross will give you this h cross square over here, and you can cancel the h cross square in all the three terms. Okay. So let us do that. You cancel the h cross square in all the three terms. Here you get just the normalization overlap, and what you have is a simple first order linear difference equation in lambda. Okay, you began with just the basic angular momentum commutation rules and you arrive at a very simple first order linear difference equation in lambda. So now it is not so difficult to solve it, there are well known techniques of solving first order linear difference equations, and you can try the solution that lambda m square is equal to c minus m into m plus 1, and if you try this solution the same prescription for lambda m minus 1 gives you c minus, here instead of m you get m minus 1, and instead of this m plus 1 you get m, and you get c minus m square plus m over here, and you get c minus m square minus m over here. And you can convince yourself that this is the correct solution because you can plug in this right hand side over here and this right hand side over here and ask yourself if the difference turns out to be twice m. It does. So our solution is correct. Okay. So this is our solution to lambda m square. C must be a constant, it cannot depend on m, but it may depend on j, nothing stops it from depending on j at this point, and that is the question that we will leave as open at this stage. So this is our solution to the first order linear difference equation, and lambda would depend not just on m but also on j, because lambda depends on c and c may depend on j. So you have to remember that. Our question now is, what is the relation between c and fj? Fj was the eigenvalue of j square, that is what we want to determine. Okay. Now let us have a look at this relationship now. Now this is an exact equality. The left hand side however cannot be negative because it is the square of a modulus. There is no way the left hand side can go negative. So the right hand side also cannot go negative, which means that in the right hand side you have three terms, you are subtracting m square which is also cannot be negative, and if this relation is to remain valid the necessary condition is that m cannot take arbitrarily large positive values, nor can it take arbitrarily large negative values. It must be confined to a certain range. It will have an upper limit, it will have an upper bound, and it will have a lower bound. So, these bounds project themselves automatically, they are not artificial. We just have to find what these bounds are. These bounds are necessary conditions, and it means that m can have a maximum value and it must always be greater than a certain lower bound. So, there are these bounds to m, but we do not know what these bounds are, and that is what we will find. Now, what we do know is that if this is the upper bound m1, m1 is this upper bound, then you cannot raise this any further. That is the very meaning of an upper bound. Okay? So, j plus operating on j m1 must vanish. Likewise, j minus operating on this cannot bring it down to a lower value m2, because there is a certain lower bound. Okay? So, these relations come automatically, which means that lambda m1 must be 0, lambda m2 star must also be 0, and we will now exploit this to find what these values must be. Now, we do have these relations because this relation is satisfied by both m1 and m2, right. What this means is that m1 and m2 must be roots of this quadratic equation, and this you know from your elementary school. This is the quadratic equation, find the roots, and these are the roots of this quadratic equation. So, m1 is equal to minus half plus half times root of 1 plus 4c, and m2 is minus half time minus half and minus half times root of 1 plus 4c. So, these come as natural roots of the quadratic equation. Notice that m2 plus 1 is equal to minus m1. From these, the relationship between these two roots is very simple. m2 plus 1, if you add 1 to m2 from this minus half, you get plus half, which means that m must be confined to this range. Okay. Now, this we have established. The only thing we have used is the commutation relation of jx and jy, and m1 is some number such that plus m1 and minus m1 are attainable bounds at the upper limit plus m1 and the lower limit it is minus m1. These are attainable bounds at the top and at the bottom. And why do you want to call it m1? You can call it anything. Okay? It is just a label, it is just a name, it is just a symbol, and this is what we relabel as j. Okay? This is the new name for m1. So, m now belongs to the range minus j to plus j, where j is the new name of m1. We still do not know what j is. We are not claiming that it must be 0, half, 1, 3 half, it will turn out to be so. Okay? So, j is the new name and m belongs to this range in steps of 1. Why in steps of 1? Because you can go from one to the next through the raising and lowering operators, which changes the m index by 1. So, it has to be in steps of unity because of the raising and lowering operators. So, we know that much. What it also means is that 2j must be either 0 or a positive integer, because this can go in steps of 1. So, the number of steps will have to be an integer. So, 2j can be either 0 or a positive integer, and this is what gives us the result that j can be either 0 or half or 1 or 3 half and so on. So, half integer quantum numbers come automatically from the angular momentum algebra. Okay? We have not used anything else, and they have a natural place, and then we still have to find out what this Fj is. So, let us complete that, and I will come back to a discussion on this point. We have to find the relation between C and Fj. So, that should emerge in a few steps. We already know that C minus m1 into m1 plus 1 is equal to 0, which means that C must be m1 into m1 plus 1, but m1 is now renamed as J. So, this is the relation between C and J. Now, if we consider the matrix element, the diagonal matrix element of J square, on J square you can express in terms of Jx square plus Jy square plus Jz square. So, this is just a matter of simple rearrangement of these terms, you can see that already, and you have the eigenvalue of J square, which is Fj, from which of course the angular momentum square has been extracted, h cross square over here. And now you use the lowering and the raising operators. Using the earlier forms, you find that you will get a term in modulus lambda m minus 1 square from this term, and from this term you will get modulus of lambda m square, right. It is very easy to see that. Now, all you have to do is to cancel h cross square, which appears in all the terms, which connects the eigenvalue f to the lambdas, and the lambdas we know, because the lambdas are in terms of C's. Okay? So, lambda m minus 1 square is C minus m square plus m, and lambda m square is C minus m square minus m. So, you put these right hand sides over here, and you find that Fj must be equal to C, which we already know is equal to J into J plus 1. So, now you have the result that when J square operates on Jm, the eigenvalue is h cross square J into J plus 1. You also know that J must be either 0, half, 1, 3 half, and so on. You also know that m can go from minus J to plus J in steps of 1. So, this is not something like a new postulate or new addition that you have to make to your set of assumptions. All this comes automatically from just the basic definition of angular momentum, that angular momentum is a quantum vector operator whose components do not commute, but the components commute according to the prescription that Jx comma Jy is equal to h cross Jz and other two relations of this kind, right. Nothing else has been used, and that is something which I think one should try to learn in angular momentum algebra, that what are the basic postulates, what are the basic considerations, and then everything else can be built from it. So, this is the fundamental thing from which you can build everything else. So, these results come automatically from angular momentum definition, and now the only thing that needs to be fixed is the fact that you have a relation for the square of the modulus rather than for lambda m itself. So, modulus of lambda m can be plus or minus square root of this. So, there is a little bit of ambiguity there. Okay? That is something that cannot be resolved from this analysis, and it is a matter of convention that one picks a phase convention. This is called as a phase convention in angular momentum algebra. This is a very important one, because different contributors to angular momentum algebra sometimes make use of different conventions, and if you do some analysis using one scheme and the remaining analysis using another scheme, and if the originators of these two schemes have used different conventions, you are going to mess up your angular momentum algebra. and I am alerting you for a very good reason, because there are lots of practitioners in atomic physics, nuclear physics, who do make use of angular momentum algebra. You are working with very involved problems, and then you need to use some results which have been produced by one group, some other results produced by another group, and if they have used different conventions, if you do not reconcile them to each other, you can end up into a very messy situation, and this is not very uncommon. So please be alert to that, always check the phase convention, and we now have these relations with the phase convention that we have adopted, and you can write this j into j minus 1 minus m into m plus 1 also as what comes under the square root as a product of these two factors. You have a similar relationship for j minus, and these are our basic relationships that we will use in angular momentum algebra. So the main thing over here is that in classical mechanics you describe the state of a system by position and momentum q and p, in quantum mechanics by a state vector. Electron is an elementary particle having some intrinsic properties like charge and mass. This q is the position, this q is the charge. Okay. So it has some intrinsic properties like charge and mass, but it may have some additional properties, okay, not just these two, and it has this additional property. In non-relativistic quantum mechanics you can describe this state by these quantum numbers. For a free electron it is a different set of quantum numbers, which are the three components of momentum. For a bound electron in the hydrogen atom, these are the three quantum numbers like n, l and m, which come from eigenvalues of the Hamiltonian, L square and Lz, right. But what you have in addition to the charge and mass is an additional quantity which is an intrinsic angular momentum, and associated with this intrinsic angular momentum is also a magnetic moment. So there is this additional property which the electron has, and you have this half integer quantum number for the electron spin, and we have got it basically using angular momentum algebra, nothing else. Now sometimes people use this to say that the electron spin has got a natural place in non-relativistic quantum mechanics. We have not used relativistic quantum mechanics in our discussion today, right. We have not referred to the finiteness of the speed of light, we have not used the Lorentz transformations, we have not used the Dirac equation, which is the signature of relativistic quantum mechanics, right. We have not done any of that. We have got half integral quantum number which can be used for the electron spin. Now this does not mean that non-relativistic mechanics provides for half integer quantum number as the spin property of the electron. It accommodates this property, it does not provide for it. There is a difference between this, and I hope you recognize this difference. The provision of the electron spin does not come from non-relativistic quantum mechanics, it comes only from the Dirac equation. You have to go to relativistic quantum mechanics, and we shall do so in unit 3, and when we do unit 3, when we do relativistic quantum mechanics, you will find that the electron spin automatically comes out neatly out of it. Okay. Here we have done angular momentum algebra which accommodates half integer quantum numbers. It does not mean that it assigns half integer quantum number to the electron, it does not do that. The assignment of the half integer quantum number to the electron spin is done by the Dirac equation, which we shall discuss in unit 3, and it is important to recognize this difference. Questions? I will like to refer you to Schiff's quantum mechanics where all this is nicely done. Yes,
slide number 24.
24. Yes.
So we assigned that M1 as J, right?
Right.
But the label J is already used. We used for the in the former derivation. So can we just directly take M1 as J?
Yeah, it did not have any specific meaning. The meaning comes now. It is just a name.
How can we think that? Both of them are.
It is just a name. You can carry this name into the eigenvalue. It is just a name, and because m can go from minus j to plus j, and this process of going from the lower bound to the upper bound has to be in integer steps, because that is mandated by the lowering and the raising operators. There is no other way to do it but through integer steps. So the difference 2j will have to be, either 0 or some positive integer, which is what guarantees that j can be either 0 or half. It is a very simple analysis and I really love it. You will find it, this is straight from Schiff's quantum mechanics, but then you do not have to learn it as an additional postulate. It comes straight from the basic definition of angular momentum algebra, of what an angular momentum is. Any other question?
The statement either if m at
Yeah. See, from c minus m you are subtracting m square. Okay. So if m becomes arbitrarily large, and m square is definitely a positive quantity. So whatever is c minus m, from c minus m if you subtract m square, then if m is sufficiently large, then this whole thing will become negative, because when you subtract a large quantity from a small number, the difference is negative. You will know it better if you think of money, right? If you have a certain amount and you take out a big chunk of it, you will be in debt. So to avoid that, and you have to avoid it because the right hand side cannot go negative, because the left hand side cannot go negative. The left hand side is the square of a modulus, how can it be negative?
statement separately in the lines. Okay,
Yeah.
thank you. I understand.
Any other question? Yes.
First order differential equation which we have, lambda m minus 1 mod square minus lambda.
Yeah, it is a difference equation rather than a differential equation.
Difference equation.
Yeah.
We had made an assumption that lambda m square is c minus m plus 1.
Mm-hmm.
So what make us to choose this condition? Because this make us something like that, we know the answer and we take it back.
Well, we do know, because these are usual ways of solving difference equations.
Are there possibilities to have some other combinations?
Not to my knowledge. Not to my knowledge. I think the solution is pretty much unique. Any other question? Mandi, Anna? Question? Okay, so thank you all very much.